Hello, everybody. So what we're going to be doing for the next few days is taking a look at some tabular free response questions from the AP Calculus test. So tabular questions have you do calculus from looking at values given in the form of a table, a la this one up here, for example. And they'll have you do things like calculate slopes from tables, find the approximate area from tables, and also maybe they'll give you some function models as well, and you'll have to actually take the derivative or antiderive those from there. But for these next few questions, we will be looking at the set of questions that I have called Domain 1. And what these ask you to do is approximate area using all of the different rectangle and trapezoidal approximation methods that we did before. So that would be the left rectangle approximation method, the right rectangle approximation method, the midpoint rectangle approximation method, and the trapezoidal approximation method as well. All right, so let's take a look. This is AP 2015 B. Do note that it's B. I think in the front page of the packet I have a typo. It says C. It should be B. But let's read the problem here. So first of all, there's no calculator on this particular question. It says that Joanna jogs along a straight path for time from 0 to 40. Her velocity is given by differentiable function v, and then selected values of v, where t is measured in minutes and v of t is measured in meters per minute, are given in the table above. Okay, so we have got a few numbers up here, values of t, and also it looks like Joanna's velocity at those different values of t. So at first Joanna was going 0 meters per minute, and then after 12 minutes she was going 200 meters per minute. After 20 minutes she was going 240 meters per minute, so she sped up in that time, so on and so forth. At 24 minutes she's going negative 220 meters per minute, which, if you recall from particle motion, that just means she's going to the left instead of to the right. And then at time 40, to finish it up, she was moving at 150 meters per minute. So anyway, let's take a look at what question number B is asking us to do. So it says, using correct units, explain the meaning of the definite integral, the absolute value of v of t from 0 to 40 dt in the context of the problem, and to approximate the value of this using a right Riemann sum with 4 subintervals indicated in the table. Okay, so let's do this second part first. Let's approximate the value of this integral. So a right Riemann sum, if you remember, is if we have a curve like this and we split some rectangles up underneath it, the height of our rectangle is determined by the right side of that rectangle. So in each rectangle we have a certain width and a certain height, and for right Riemann sums, the right-hand side of the rectangle determines the height. So as I go to look at the table here, you see that I have 4 different subintervals. Here's the first subinterval, 0 to 12. Second subinterval, 12 to 20. Third subinterval, 20 to 24. And the fourth subinterval, 24 to 40. And what we're going to do is set up our right rectangles for each one of those Riemann sums. Okay, so let's do the setup here. So for part B, let me try that again. There we go. For part B, let's say that the integral from 0 to 40 of the absolute value of v of t is approximately equal to, and then our first rectangle here looks like it's going from 0 to 12, so its width would be 12. And then to find the area of a rectangle, we multiply by the height of that rectangle. So the height of this rectangle would be based on the right-hand side, which would be 200 in this case. We'll go to the next rectangle. So the next rectangle would go from 12 to 20. That width is 8. And then the height of that rectangle would be 240 plus. The next rectangle would go from 20 to 24, so width of 4, and with a height of negative 220. Oh, so it says it wants us to do the absolute value of velocity here. So what we would do then, instead of doing negative 220, is we would take the absolute value of negative 220, which of course is positive 220. I'm just going to write it as the absolute value of that here, just so you know where I'm going to switch it to positive. You don't need to write that yourself. And then the last rectangle here looks like it has a width of 16 times, and then a height of 150. Okay, so let's just explain what this whole thing would be equal to. So first off, you don't need to simplify really anything on the AP test. So really all that we would generally have to do is, once we write all of these numbers right here, and what I might do is I might just rewrite them as all positive without the absolute value. There we go. And then I would box them up like that. And there we go. We've earned like 2 points on the free response question. The second part of this question is asking us to explain what this integral means. In order to better see this, think about what each part might mean. So this first part, the 12 times 200, means that for 12 minutes, Joanna jogged at 200 meters per minute. So if you take 12 times 200, if you were to actually do that, that would mean that she jogs for, let's see, 10 times 200 is 2,000 plus 400. That'd be 2,400 meters, because meters per minute times minutes is meters. So in that time, she traveled 2,400 meters. So if you take all of these pieces and add them together, what you would end up with is the conclusion that this is the total distance traveled And then very important that we do this last step as well. You see it says using correct units. So we're going to say the total distance traveled in meters. Okay, that is a pretty standard area approximation problem. Why don't you take a look at a few of the other ones in the first subpath yourself, and remember, you can always check your answers by just Google searching the particular problem year and solutions and take a look. All right. Hey, welcome back. So in the second set of problems here, we get a little bit more difficult, mainly in that we're seeing some different integral patterns that we would have to interpret the meaning of these. So in this particular part, I'm looking at AP 2012, part C, and then you can also see that it requires a graphing calculator for this particular problem. It says, for time from 0 to 20, the average temperature of the water in the tub is given by this integral. And then we need to use a left Riemann sum with 4 subintervals indicated by the table to approximate that integral. And then what we're asked is, does this approximation overestimate or underestimate the average temperature of the water over these 20 minutes? And then to explain why. Okay, so what I'm going to do is take a look back up at the original problem. I see I've got a table right here. It says the temperature of the water in the tub is modeled by a strictly increasing twice differentiable. That means that W double prime is a thing that exists. And then W is measured in degrees Fahrenheit and T is measured in minutes. And then at time 0, the temperature is 55. We know that from the table. Then the water is heated for 30 minutes beginning at 0. But our table only goes up from 0 to 20. Okay. All right. So in part C, let's set up our approximation for this integral expression. Now, this is just straight up telling us that this particular integral is the average value of the temperature of the water in the tub. In the future, you will want to know that this fraction in front is a big hint that what you're calculating is the average value of the function. So you'll want to be aware of that for future approximations. All right, so we're asked to do a left Riemann sum here. So that means that if we have a function that looks like that, the heights of our rectangles would be based on the left endpoint, like this. So we would have widths of rectangles, and then the heights would be based on the left endpoint. Okay, so let's set up our 4 rectangles. So I'm drawing my intervals in here, as you can see. So my first rectangle goes from 0 to 4. So its width is 4. And then the height of that rectangle would be based on the left endpoint there. So it'd be 4 times 55.0 plus. Then the next rectangle would have I'm going to put parentheses around this 55. I think it looks better. And then our width would be 5 for the second rectangle. And the height of our second rectangle would be 57.1 plus. And then the width of our next rectangle is 6 from 9 to 15 with a height of 61.8 plus. And then our last rectangle is a width of 5 with a height of 67.9. Now this last thing is very important. You remember that there is a 1/20th out front of this integral right here. That means, and maybe I should have done this first, but I definitely want to make sure I remember this, is in the end, we need to multiply this whole thing by 1/20th, or basically divide by 20 for what we get in the end. So let's go grab our calculator and calculate what this would be equal to. All right, so after taking a few seconds to calculate that, it looks like our numbers in the parentheses would end up being 1,215.8. And then I need to remember to divide this by 20, or multiply by 1/20th. And we end up with 60.79. And then the units on this, I need to remember, this is an average value, so the units on this would be degrees Fahrenheit. So the average temperature of the tub, that's what this is the average temperature, is 60.79 degrees Fahrenheit. Now, what's left is that we need to say whether this is an overestimate or underestimate. And here's the key piece of information. So it previously mentioned that this function was strictly increasing. So take a look at this picture that I drew right here. This function is strictly increasing as well, and as you can see, all of the left rectangles lie below that function. That's our key to this. So we would say that this is an underestimate because W of t is increasing. If W of t were decreasing, then our left rectangles would be an overestimate. If we were using a right Riemann sum instead, imagine what the rectangles would look like. They would go all the way up and then go over like this. So if this were a right Riemann sum with an increasing function, we would have an overestimate. So that's how we handle that. So try some of the other area problems from the second part of Domain 1, and if you'd like, I can meet you back for the last group. Okay, so in this last group, you'll be expected to not only use some tricky area approximation like trapezoids and midpoints, but also possibly make some conclusions about how to set up these integrals. So it says in this problem, the height of a tree at time t is given by a twice differentiable function h, where h is measured in meters and t is measured in years. Selected values of h are given in the table above. Okay, so this table right here. And then what we're doing right here is we're looking at part C. So use a trapezoidal sum with 4 subintervals indicated by the data in the table to approximate the average height of the, okay, so that's important, average height of the tree over the time interval 2 to 10. All right, so here's what we will do. For the average height of the tree, remember our discussions in the previous problem that the big hint for any average value problem is the fact that you've got an integral going from whatever your bounds end up being, and then you've got a fraction in front which indicates that you're dividing by that time. So our integral is going from 2 to 10, and we would then have a fraction in front that would be 1 over 8, because the width of this time is 2 to 10 is 8. So 1/8 of that. This integral should give us our average height. If you didn't know that, you can still get some points from this problem by setting up a trapezoidal sum and just doing your best with the information that you have. Every single time they will tell you trapezoid sum, right Riemann sum, left Riemann sum, and if you set that up at least, then you will get some of the points for that. So let's set up this trapezoidal sum. Keep in mind that this is a number 4, and that makes it a no calculator problem. So let's just set up the trapezoidal sum and see what we get. So we've got 4 subintervals, interval 1, 2, 3, 4. As you can see, our t is on top and our h of t is on the bottom. So when I set up trapezoids, remember that the area of a trapezoid, I draw a little trapezoid right here, is height 1 plus height 2 divided by 2 times the width. So width times height 1 plus height 2 divided by 2. So what we would put this as is, for our first trapezoid, we would take our width, which in this case goes from 2 to 3. So that would be 1 times. And then our first height is 1.5 plus. Our second height is 2. And then we divide by 2. There's the area of our first trapezoid. Plus. Now we do the next trapezoid. We're going from 3 to 5. So this trapezoid width is 2. And then we would do the heights again as well. So 2 and 6 divided by 2 plus. Our next trapezoid goes from 5 to 7, so we're going to set that up similarly. We're going to use the 2 heights again, 6 and 11 plus. And then our last trapezoid is going to have a width of 3, and that would go from a height of 11 and a height of 15. Okay, as you're doing these, remember to be reading the heights from the y column, or the dependent variable, and be reading the widths from the independent variable t. And then remember that for this particular integral, we've got a 1/8 out front, so we want to make absolutely sure that we multiply this whole thing by 1/8, or divide by 8. And then in the end, you don't need to simplify anything. You've got all numbers here. You can just box this up, and that would be that. There we go. The key parts of this problem are knowing that for average height, you need to have a fraction in front of your integral. You need to divide your integral by the length of time that you were integrating over. And then the other key to this problem is knowing that your trapezoid area is width times height 1 plus height 2 divided by 2, and that you don't need to simplify all those trapezoids together. This is good. All right. Thanks, guys. Remember that if you have any questions or if you need to look up solutions, feel free to just do that on Google. It's a fantastic resource, and that also would let you see some of the scoring guidelines as well. If you have any questions, please send me an email or just find me and ask me. Thanks.